students, teachers, and good afternoon, sir. So today we have our own Anand sir here with us to give a talk on, sir, math, science, and life. Am I right? Yes. Welcome, sir. So I'm sure we will all have a very enriching session, and I'm sure Anand sir will enjoy presenting it as much as we enjoy listening. I would like to say a few words about Anand sir. You all know him, but still, which certain things which you may not know. Sir studied in an ICSE school in Kerala and came to Chennai for his college education in Madras Christian College, where he studied physics from 2002. He was far more interested in music than academics while in school and all throughout his college days. Right after college in 2009, he joined Goddard School as a physics educator. 2 years into teaching, he was also asked to teach music to children. He continues to teach physics and music at Goddard School since then, except for one academic year, 2016-17, when he taught in NPSI Chennai. So that's when we all came to know about him, and he made a mark in our school that we all still remember him. He enjoys teaching physics with the use of technology and loves to solve physics problems and perform experiments. He loves to sing and to play the piano. He loves it even more to teach children to sing and enjoys it when the children sing together. As a kid, he grew up playing computer games and continues to do so even today. He loves to fix things that are broken and is crazy about technology and machines. This is nice, children. This is very interesting. He has three wild dreams: to become the drummer of a semi rock band with his friends and tour the world playing music, to own a full fledged workshop where he can experiment with wood and metal work to make furniture and other things. And the third one, even more interesting, to fly a Boeing 737-800 and land at Chennai airport. Sir, I wish all your dreams come true. Over to you, Anand, sir.
Thank you. I just want to ensure that you can all hear me clearly and you can see me. Is that okay?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so this is the first time, like I was saying, this is the first time that I have been invited to talk to a place other than where I work. So I have to say I'm very nervous, and I'm all the more nervous because there is this technology that's coming in between us, and I'm staring at two monitors and my empty cell phone here and this one. So it's a little, we are all getting used to this sort of thing. But one thing you can do is in the middle, when I'm talking, whenever you have a question, I think you should feel free to stop me and ask. And I would like to keep this a little interactive. And I also did mention to Prabha ma'am, if maybe just one or two or three of you could just leave their or videos on. There'll be some that would be some kind of a reassurance to know that people are there and I haven't lost connection. That would be quite reassuring. What in particular I want to say, I'd actually thought of three things, but I'll cut it short to just two. Uh, I'm not going to talk about something very profound and very fantastic. I'm going to talk about some very simple things. I'm going to talk about two very simple things. Okay, I'm going to talk about making connection. Okay, and I'm going to talk about very simple mathematics. In fact, that simple physics was part of the last bit, but which I may not talk to due to lack of time. But I am surely going to talk about our lives and how these things are interconnected. Right now, two simple ideas. Okay, and this uh, first idea, I'm going to tell you something that we do in the physics lab, right? And how we can connect that to real life. And the second one, I will talk to you about something in real life, how you can connect it to mathematics and physics. Okay. Now, the point here is so that I can encourage all of you to know that there are such connections all around us, right? It is just waiting to be discovered and to be enjoyed by each one of you. That's the point. And so, to which you might turn around and ask, why is this important? And so, in my opinion, this is important because personally, for me, finding such connections, which you will see are very simple connections, has helped me learn and teach and understand mathematics and sciences much better. And in fact, to a certain extent, music as well, right? And of course, whenever you come to talk about math and science, you're always worried. I'm at least very conscious because I have students who find math and science quite difficult for their own reasons. My job is to try and make it as simple as possible for them. Here, for those of you who think that they find math or science very difficult, I want to reassure you that I'm going to keep it very simple. And this is a very simple exercise which only requires your attention and your interest. All right. It doesn't require any higher order thinking skills or anything like that. So I will start by asking you the question, right? And please do feel free to stop me at any time. And let's keep it as interactive as possible. So this is the first question. All right, this is straight out of the physics lab. This is where I wanted to ask class 9 students who are here. Have you by any chance done this experiment in the lab where you find the time period of a pendulum and then you thereby find the acceleration due to gravity? Have you done this experiment in the lab? Anybody in class 9? You have done it. You have done it. So who is this speaking? Could you introduce yourself?
I'm Suchita, sir. I think you know.
Sorry, dear. Could you speak up a little bit?
I'm Suchita, sir.
Suchita. Yes, Suchita. Could you tell me, would you be able to tell me what was the content of the experiment? What did you do? Do you remember?
Sir, can you give me a minute to think?
Yeah. Okay. Somebody else in class 9 would like to answer by the time Suchita can get back to us? Yes, Samyukta has put up her hand.
Sir, is it because it's probably easier to find, to divide the time by 10, and because
no, that's not my. I will come to this. You are answering the question on the screen. I will come back to you. My question is not that now. My first question is, could you tell us what that experiment was all about? What did you do in the experiment?
Oh, so we needed to find the time period after.
Okay. And how did you do that?
So we let the pendulum, the pendulum oscillate 10 times, and then we calculated the time it took, and then we divided it by 10, and we got the time period.
Okay. So now that you have all seen the question, I'm just going to stop my sharing and I'm going to turn my camera on. Somehow I'm not able to. Now you can all see me, I presume. All right. So thank you for that. So you said we oscillate the pendulum and we take time that it takes to go back and forth 10 times. And then we repeat that a few times. And then we take the average of that time, that 10 oscillations. And then we divide that average by 10 to get the time period of a single oscillation. Is that right? Is that right?
Yes, sir.
Yes. All right. So the question remains, which is the question that I'm trying to ask you. Why is that? Now you can answer. I think Samyukta, you were trying to answer that. Maybe you yourself can answer. Why is that we do this oscillation 10 times or 20 times or whatever it is that you do? Could you answer, or anybody? Yes, Rajesh.
To reduce the error value that you will record.
How exactly does that happen?
Well, say if you were to record the time period for one oscillation, you're going to get an error value of, let's just say, 0.2 seconds. So the more you do, you have more number of oscillations. So you don't have, so the error value will decrease more and more by depending on the number of oscillations you do. So say to be the error value divided by the the expected percentage of error value.
Okay. Somebody from class 9. Rajesh is in class 12. I want someone from class 9 who can throw some light. Anyone? Okay, never mind. All right, I'll go ahead. In fact, I just want to quickly show you. This is exactly how we make connections now. If you can see my screen. So this is my next question to you. Can anybody answer this question?
Obsessive-Compulsive Disorder?
Yes. Who is that? Rahul?
Rahul.
Yes. Rahul, could you tell us what obsessive compulsive disorder is?
It's like you have a abnormal fixation on a particular thing. Like, for example, keeping things organized. That's kind of what it is like.
Okay, good. So, what do you think this this pendulum thing and OCD has a connection? So this is how we connect things, randomly, just for fun. Yes, go ahead.
It's like a person with OCD would be better at the experiment because they would take more data and get a more accurate result.
All right. So let me tell you, do you think this thing that I'm talking about pendulums and OCD, you're saying a person with OCD. Oh, by the way, those of you who don't know what OCD is obsessive compulsive disorder. And I have to confess, I have a tinge of it, right? I've not been clinically diagnosed, thankfully. I have a tinge of it. I get it from my mother. And I see that my daughter also has it a little bit, in the sense that, we are kind of perfectionists. We want everything to be absolutely, and if it is not, it kind of it kind of worries, yes, somebody put their hand up. Please go ahead. Who is that?
Oh no, sorry, sir. That was an accident.
All right. No, never mind. So here's my next question. What do you think this has to do with making dosa?
Nothing at all.
Maybe that's what you think.
I wouldn't say nothing at all.
Perfect circle or something.
Perfect circle.
Yeah.
Perfect. Okay, that's something I didn't think about at all. When I was preparing for this. All right. But let me go ahead anyway. I'm going to tell you how I make dosa. Okay. And in fact, this is the only thing I'm proud to say, that in terms of cooking, I'm better at making dosa than my wife. Okay. And it's kind of become a problem, because whenever there's dosa, she said, "You go and make dosa." Okay. Otherwise, she'll be the one cooking for me. Anyway, and I have to say, my daughter also loves the way I make it. I have done it enough number of times to experiment, see what combination goes in to get this thing just right. But let me tell you how I make dosa. And for all the people out there like me who loves to eat food, yeah, you will really appeal to this. That is to say, I get a 1 kg pack of dosa. It comes now. Earlier, when my mother used to just make it at home, I don't know how she does it. I don't know I'm sure most of the teachers here know how it's done. Most of them even now make dosa they don't buy dosa maav from outside. Instead, take the rice and put it in the mixie and get it done. Anyway, I buy it from outside. It comes in a cover. All right. Now, what I do is, when I make the dosa, and say I take, I buy a 1 kg cover, and I can make about 15 dosas with it. Supposing there are 4 or 5 people in the family, that 15 dosas should be, sufficient. And you see, when we're making this dosa, and you take the batter out of this, and this is going to be very real life thing. Okay, when the batter is almost over, when you reach the last dosa, what you do, you see, a lot of this dosa batter is sticking on the walls of if it's the plastic bag, it will be plastic bag. Means this company called ID that makes rather high funda bags, right? So they all stick to the walls of it. So you wash your hands and then put your hand inside, and then you will scrape the walls, and then you want to take the very last drip of that maav coming out. And someone like me, I have to do it. I just cannot take that thing and put it and wash it in water and see all that maav go to waste. Okay, I just cannot. So I have to do it. All right. Now I have this question. Why am I talking about all this? Because I was speaking to you about pendulums. All right. So let me just show you, and in showing this thing about making dosa, I might throw some light into how this pendulum things work and that error thing works. Okay, so let me just get my pen. I hope my color right. Okay, I presume you can all see this. Can you see this cursor move?
Yes, sir.
Yes, sir.
All right. So let's say I get a 1 cover. I'm sorry, my artistic skills are rather bad. Should get me to sing. I can do that much better than this. So say this is the dosa. Let's call it this ID, and ID is not sponsoring this video, but anyway, and say this is 1 kg, which is equal to 1,000 gram. On a regular basis, when someone who's not OCD like me, when they finish all of this 1,000 gram, they're not going to put their hands inside and scrape it and things like that. For instance, my wife never does it. Okay, and then I have to intervene, catch that thing before she puts it into the sink to pour water in it, and then I have to push her out of the way and make that last kutti dosa, which will give me that immense pleasure. Okay, so on a regular basis, say a person who does it, say you make about 15 dosas. Okay, and the last at the very end, say some 50 grams is wasted. Okay, instead of GM is very wrong, should be 50. So my question to you is, how much has been wasted? Well, that's not rocket science. You had 1,000 grams, you wasted 50 grams of that 1,000, so you consumed 950 grams. Now, if you look in terms of percentages, you say that you're wasting 50 grams out of the 100 grams. And if I want in percentages, I multiply that by 100. And what would I get? I can cancel these 2 zeros and 3 zeros here and 3 zeros here, and I get my answer as 5%.
5%.
All right, very good. Now, at this point, I have to ask class 9 students are there. You are all following, I presume.
Yes, sir.
Yes. Yeah.
Yes,
so, very good. Thank you very much. So this is a 5% wastage. Now, on the other hand, when I do it, I don't waste 50 grams. I am very careful. I may waste about 10 grams. All right. And so what is the wastage that I come across? So you this cancels, these three cancel. In fact, if you don't know the physics, you must know this gram also cancels and gives me a 1% wastage. Is that okay? Now here's a question. Suppose look at that again. So the wastage is 5% for a regular person and 1% for someone like me who has a tinge of OCD. Oh, ODC, sorry. Sorry, OCD. All right. Now let me ask you a question. Supposing we don't make 15 dosas, but instead I want to make, say, 75 dosas. There are a lot of people who have come to visit, and I have bought now not 1 kg but 5 kg of dosa. Dosa, of course, it's the dosa batter, right? Now, what do you think is going to be the wastage here at the end of it all? Say, for instance, you take it in a large vessel, and this was the same vessel that you used earlier also, or out of the packet, or however you want to call it. Now, you might now at this point say, no, sir, you don't get it in 5 kg packets. You have to buy 5 separate packets. Fine. Now, let's consider a situation where I take it out of a single large 5 kg, a vessel, right? And when I empty it, I find that there is some stuff sticking on the walls of this. Okay, there's some stuff sticking on the walls of this. And if it is a regular person without OCD, well, that person you can say, because it's been a lot more, because if I take 1 kg, in the same vessel, it would be only 1/5 of that. So the wastage surely for this is a lot more, because there's more sticking on the wall. So let's be a little generous and say that this person wastes not 50 grams like last time. Let's say that person wastes about 100 grams, managed to scrape some of it out. Yeah. Okay. Or let me not be that generous. Let's say 200 grams is wasted. Okay. Now, you see, this is the 200 gram wasted. On the other hand, if I were to do it, you know what I would do? I am still very much with my OCD. I will scrape it so clean that I will leave only a little bit of dosa at these corners where my fingers cannot reach. Okay. And I will scrape everything out, and I will make sure that I will, maybe about 20 grams. Or, in fact, ideally speaking, I should say that I will waste that same 10 grams only as I did the last time. Okay. So now let's do the math and see how much wastage is there. So this is the second scenario where we have used 5 kg of dosa batter, and I have the regular person is wasting 20 grams divided by the 5 kg, which is the 5,000 grams. I'm sorry about this. I shouldn't put that M there, right? And what percentage is that? The grams will cancel, 3 zeros here, 2 here, and 1 here. And if I divide 20 by 5, I get there's a 4% wastage. Well, that's not bad. You see that from 5%, wastage, when you're using 5 kgs to run your show, you waste a little less. But what about me, the guy with the OCD? Yeah, the guy with the OCD, he still wastes only that 10 grams. All right, out of the, he spends, like someone like me spends a lot of time cleaning that plate with their hands. Yeah, that people might come and think that, oh, this is actually a clean plate and let's use it again for something else, you know. And in fact, that's a story, it's a real life story. It did happen once. After I finished eating my food, my brother came and ate on the same plate, thinking that it was just a fresh plate kept there on the table. Okay, so look at that. What percentage is this now?
Sir?
3 zeros cancel. 1 second here, and this cancel giving me 1 by 5%, which is 0.2. Yes, somebody called me. Tell me.
No, sir, you wrote 5,000 kgs.
Oh, I'm so sorry. Thank you very much. Thank you very much. Slip of that happens very often. Please point it out. Now, do you see that? Do you see that? Do you see that? You see how the wastage has gone down from 1% to 0.2%. That is 1/5 of the total usage only. So the moral of the story is, the more you use, looks like if you have to run through a large amounts of this, those are better. Say, for instance, you are running a restaurant where you're not using 5 kgs, but you're using 50 kgs, right? And you use it out of the same vessel the whole day. Yeah. Well, I don't know how hygienic that is, but I think one day or maybe half a day, you know, keeping on mixing dosa into one large vessel. I mean, doesn't seem too bad. I'm sure most of the 5-star hotels also do something of that sort. Anyway, so the more you use, your error rate comes down, even if you don't have your OCD. Right? Is this point clear to all of you? Is this point clear to all of you?
Yes, sir.
Yes. All right.
Yes,
so
sir.
now let's look at the oscillation. Now let's look at the oscillation. You see, somebody Ragesh was telling that there is error. Okay. So I would like to point out, say for instance, I am conducting this experiment where I have 20 oscillations. I'm doing 20 oscillations. So which means, you see, I'm very bad at doing experiments. I'm very sloppy. So when the oscillation starts, I don't start my stop clock at the exact time where I want to measure it. I either delay it a little bit or I'm too early. Okay. So for this first reading of time that I take, there is always an error. There is always an error. I'm going to call that E1. Okay. That error in the first reading. Right. Then after that, what happens? After that, nature takes its course, and all of these, and all of these oscillations or swinging takes place without any disturbances, right? And each of those, let me call this T2, T3, T4, and so on. These are all the time taken. Of course, not to mention that T1 must be equal to T2, must be equal to T3, must be equal to T4, because it's an oscillating pendulum. Every swing will take the same amount of time. And in the last swing, the 20th swing, you see that it takes that T20 amount of time, which is also should be equal to this. But because I'm sloppy at doing my experiment, I might take a little more or a little less, and I would like to call that error E. All right, E2. Sorry. Now let me do the math. Now. So how do I do my calculations? I say my calculated value of time period must be equal to that first time plus or minus that small error, right? Plus then T2 plus T3 plus and so on all the way to T19, right? This is all undisturbed, no problem. Plus that last one, which is T20 plus or minus E2, that second error. And I have to, this is the total time I will see on my stop clock. This will be the total time I will see on my stop clock. And I have to divide that by 20 because I took 20 oscillations to get the value of the calculated value of time period for a single oscillation. Yes or no? Are you follow this? I mean, I'm sorry. Are you all following this? Class 9. I'm more concerned about class 9. I'm
Yes,
sure
sir.
all the others have done this. You follow this math, right?
Yes.
Very simple. Very simple math. There is no rocket science involved. Now, this I would like to rewrite this a little bit, and I would like to write this as. By the way, don't forget that Nature takes care of this. I don't have to do anything about this. Nature takes care of the fact that these time periods are the same. The only problem is this error that takes place because I am not good enough to measure nature accurately. Yes or no? Yes or no?
Yes, sir.
Yes.
Yes,
So
sir.
good. So these are all equal. So then I can write this t, this calculated value must be equal to, I'm substituting all of these numbers with a single t. I'm going to call it just the time period t. So here it will be t plus or minus that error, right? Plus, and all this put together should give me 18t. Yes or no? Add the last time period, the t20, which will also be the same, but because I am sloppy at my experimenting, there will be a small error. And this, I'll have to divide this whole thing by 20 to get my actual value. Do you follow this? Do you follow this step?
Yes, sir.
Okay, now it's very simple. I'm just going to, there's no multiplication here, it's just adding things. So whether I add a plus b plus c or a plus c plus b or any order, it's no problem.
Commutative property.
Yeah, that's right, commutative property. So I'm going to add these three things. Surely I'm going to get 20t, right? And plus or minus E1 plus or minus E2. Yes or no? And the whole thing, of course, I have to divide by 20. So let me just take the next one. Did you? I just have a look at that for a few seconds. I hope you follow the math, right? Next step. So next step is this t cal. I'll just write that last step all over again. I write that 20t plus or minus E1 plus or minus E2. Why plus or minus? Well, I could have pressed my button a little later or a little earlier. I'm not sure of that. Okay. And then I divide this by 20. This is what my time period will be. Now, let me combine these two errors. I don't want to call them E1 and E2. Let me just call it E. Just some error. I don't know what that is. Maybe plus, oh, this should be capital T plus or minus some E. I'm going to combine these two and call that as E. Okay. And divide it by 20. So what is my final answer? T cal is 20t plus or minus E, the whole divided by 20. Now what? Now you know these properties of fractions where I can split this into two separate fractions.
Yeah, so it's t plus.
Right.
So always you get t by error by denominator.
That's right. So now look what you get. Those cancel. I get the actual value. It should have been this plus or minus that error divided by 20. Now do you see why we do it 20 times? Because if I had done it 100 times instead, this expression would have been t1 plus E1 plus or minus E1 plus t2 plus t3 plus and so on all the way to t99 plus t100 plus or minus E2. Correct? And the whole divided by, instead of 20, I'll have divided by 100. So much so that this expression here will become t plus or minus E1 plus 98t plus t plus or minus E2, the whole divided by 20, which will give me 100t. When I come back here, this would become 100t plus or minus E, the whole divided by 20. Because you see, whether I take 20 oscillations or 100 oscillations, that error that takes place only in the first swing and the last swing, nowhere else. And however bad I am, I can do only so much error. That error will be same whether I do it for 20 oscillations or for 100 oscillations, because you know I am doing it only for the first and the last. Are you following this?
Yes,
right? So that's the idea. So if I do it for 100 readings now, my error is going to be so much less. Because then if I were to do it for t cal, let me call it t cal 20, t cal 100 would be t plus or minus the same error divided by 100. And this, as you know, is 5 times more accurate than this. That is why we take more number of oscillations. Do you follow this now?
Yes, sir.
Right? So you see, the mathematics of this works exactly like the dosas that you get. The mathematics of this works exactly like the dosas that you get. The more dosa you run through your system, the less wastage. The more oscillations that you make, the less error in your final answer. Yes or no? Are you following this?
Yes,
Are you
sir.
following?
That's why medical testing has a large sample client, like a large test base.
You mean to say you're not talking about medical testing, or are you talking about
like drug trials and that kind of thing?
Drug trials, that's right. You have to run it through. In fact, the latest being that the Oxford drug trial has been stopped because out of the 10,000 people that were given, 1% developed some spinal infection, inflammation, I think, and they've stopped the trial now. We'll keep our fingers crossed and hope that this whole thing gets through. All right. So are you following this? Do you have any question? If you don't have, I will move to the next one. In fact, I would like to stop the sharing and share my video for just a second so that you can all see me. I know that just listening to some voice, it's almost like listening to an audio book. Okay. Any questions? No? All right. Okay, we can push questions to the end anyway. So what did I do here? I told you a scientific phenomenon and I connected it with something that we do in real life, right? And there is a connection between the two. Okay, I had this thought, of course, I mean, to tell you very frankly, the first time I thought about this, it was never dosa. I saw a lady making eggs on a roadside street. But of course, I thought for my, I didn't want to offend my vegetarian friends, so I decided to shift it to dosa instead. Okay, that's the idea, right? On the lighter side. All right. Now, so now the next one. So here I asked you the question. The first example, I asked you the question, a scientific question, and I showed you the relation to real life. Now I'm going to turn that around. I'm going to ask you a real life question, and then I'm going to show you the science and the math behind it. All right. And just like in the previous case, I think all of you knew the answer. Why do we take more number of oscillations? To reduce the error. Of course, you haven't gone through maybe you never went through the details of it, but you all knew the answer. So in the same way, the next one also, I assure you, all of you know the answer for this. So let me present my screen again. The mathematics of a bumpy ride. What is a bumpy ride? Anybody?
The amusement park thing where it's like.
Well, not really. That's not what I'm talking about.
When you travel on
like potholes and like
when you
like
travel on
potholes,
Indian roads.
irregularities.
That's right. You said it when you travel on Indian roads, right? Yeah, we have such regard such regard for ourselves. Okay, so this is the question. Where on the bus should I sit or stand in order to experience a least bumpy ride?
The
you
middle?
Understand what sorry?
At the middle.
That's right. Well, like I said, I think
Yeah,
everybody knows the answer to it. You all say, where should it be? Tell me.
in the middle.
In the middle. In the middle. You're right. Right?
Yeah.
Most of you know the answer to this already. But here my question is,
Weight is balanced.
the weight is balanced. Okay, let's see. Let's see what the answer is. Let's see. Now, the question is, can you say why this is the answer? And in other words, can you prove it? And when I say prove it, I mean you have to prove it mathematically.
You can't just use angles. We can do it, sir. I think. Like I believe, like if we use let's say we keep the center of an angle at a wheel, and like if we take the other wheel, we can show that like it will bounce a further distance than a point closer to the wheel.
Correct. Very good. That's very good. Aditya, your name is Aditya.
And if like do that, yes, sir.
Yes, Aditya. That's which class are you in?
11th, sir.
Okay, Aditya. I'm not sure. I know you. I remember an Aditya.
Yes, sir. I don't think. Yes.
Yeah, you joined much later. All right. Thank you, Aditya. That's just about it. That's just about what it is. So let's look at this. I'll take you through this whole thing very carefully. So the first thing I do, and by the way, how did I come across this? Again, when right around the time my daughter was born, I had to travel back and forth to Kerala a lot. And that was the time when I had the worst kind of back pain because of a back condition that I have. And every time I get into a bus, I had to ask myself the question, where should I sit in order to experience least amount of pain? And that's where in one of these bus trips, I figured this out. Okay. So you see that is the center point. I've marked a perpendicular to the center point. I'd like to call the distance between the wheels as D. D for donkey. All right. Small d. All right. Now, what happens when the bus goes through a bump? Let's say there's a speed breaker on the road, and you see the first wheel goes through it first. Yeah, the front wheel goes through the thing first, and as you can see, it will be pivoted. The back wheel will be pivoted, and this thing kind of goes up and then comes back down by the time it gets over this, right? So in this, mind you, the wheel should have actually been here. and this being the distance d. But because of this bump, now the wheel has gone up and it traces a small arch, as you can see. So much so this is a part of a circle. I would like to call it the pizza, right? That's the pizza of the circle. All right. So I like to call it the pizza. So as you know, on the both sides of the pizza will have the same length because that is the radius of that full that full circle that it should have traced. All right. So it goes. Now I would also like to add one more variable here. We call it h, which is the height through which it raises, the vertical height through which it goes down. Not the length of this arc, not the length of this arc, but the height through which it goes up. All right. And then after this, what happens? The front wheel goes through. So look at that. You get this shape, this pizza shape where you have both sides are equal, and then you have the height through which it races. Of course, this point here, this line here has to be horizontal. That's the idea. All right. And then after the front wheel goes through it, the back wheel will go through. Right, and the back wheel will form a symmetry in the sense the previous one, this is the mirror image of this, so to speak. If you reflect it about this point, about the center point, that's the idea, right? Do you follow this? All of you follow this and this?
Yes, sir.
Very good. So now what I'm going to do is I'm going to look at those two pizza pieces together carefully. All right, and in order to find out, and mind you, don't forget, what are we trying to find? We are trying to find out where should I sit in the bus, where I should sit in the bus. Where should I sit in the bus in order to experience the least bumpy ride? There, go back there. Where should I sit? Okay, so let's do that. I think all of you know the answer is the center. And let's see how we can arrive at that. And we have to prove this beyond any doubt. We have to prove it mathematically. So in order to do that, I'd like to superimpose these two pizzas together like this. And now can you see which of these points on this line or this line has the least amount of displacement from the ground? If I take this point, you can say, yeah, look at that. See, it goes only so much up. But you see, that's when the back wheel goes through. But when the front wheel goes through it, it has to go all the way up here. Yes or no? Yes or no? If you take some other point here, I see that, well, when the front wheel goes through the bump, it goes up only so much. But then when the back wheel goes through it, it has to go all the way up here. Correct? Correct. That way, if you look, you see that the point joining these two pizza pieces is the point that goes the least. Whether the back one goes or the front one goes, it goes the same length. And that, from this, you can see is the least height that it goes up. Yes or no? Do you follow this argument?
Yes,
Do you follow this argument?
Yes, sir.
Yeah.
Yes, sir.
All right. So therefore, let me draw a perpendicular. We'll drop a perpendicular to the horizontal here. Then surely those two angles will be 90 degrees because it's a perpendicular. And then I'm going to call this angle theta and this angle theta. Why are these two angles the same? They are same because this height and this height is the same. Just reiterate that. Just go back and see. That's the height through which it goes up. If you consider both the wheels to be of the exact same size, surely the height through which the front wheel goes up is the same height through which the back wheel goes up. This will not be true for a tractor, say so to speak, where the back wheel is much bigger than the front. Okay, so we are just, of course, we don't ride long distance by tractors, thankfully, right? So we will just discuss just this. All right. So these two are thetas because we two are head. I would like to call these points A, B, C here, and this point as P. All right. Now, who was Aditya? You were the one saying. Could you take a guess as to how I'd like to proceed with this? Could you take a guess as to how I'd like to proceed with this now?
Okay. Like I'd say, like take the heights at if you're using it at angles, it basically be like taking the midpoint where the sum of okay. Like how I would go about it, I'm like I'd basically graph out the sum of the heights at the same point of both the AC like of both the angles, and I really take the point where the sum was the lowest, and I'd sit there.
All right.
And
okay.
Like,
now,
and that'll be exactly the middle.
Right. That's but can you prove it's exactly the middle? How will we prove it? You're saying this point P must be the midpoint of A and C, correct?
Yeah, yes, like it's what I'm saying. Like, if we graph out the sum of the heights, we can basically.
Yeah. So good. You know, in fact, as what you're saying is right, and as an exercise, you should try and do that because there is no one solution to a problem. There are several solutions, And
Yes,
this
sir,
is the solution.
different.
The following is the solution that I would like to say. I want to prove that this triangle here and this triangle here. Oh, well, let me see. I think there's a laser pointer somewhere.
Okay, in that case, we can do it easily, sir.
Yeah, this laser
like
pointer.
assuming like
this triangle here, ABP and CBP. I would like to prove these two are congruent. I'd like to
That's
stop
easy,
at
sir.
this point and ask class 9 students, have you studied congruency?
Yes, sir.
Okay, what do you mean? Who is that? Who said yes? Could you tell me what is the meaning of the word congruent?
So can you repeat your question? I'm not able to hear you.
Yeah,
very
my
clearly.
question is, you said that you have studied congruency. Could you tell me what
sir.
congruent means?
So congruency is basically that when the sides and angles of one triangle are the same for another triangle.
Right. Not the same, they're equal. Let's get a little more mathematical about it, right?
Okay.
Mean to say that two triangles are absolutely alike in all aspects. Yes or no?
When superimposed.
Well, yes, when superimposed, right? Or well, you don't have to superimpose it. The angles are the same, they're equal. They will be equal. All right. So here is my question to you. Could you help me prove that these two triangles are congruent?
Okay, sir. I'm not really sure.
Okay. Anybody else? Somebody else who would like to try from class 9? I know that the senior students.
Can I try?
Yes. Who is this? Aparna?
Suchita.
Sorry?
It's Suchita.
Suchita. Yes, Suchita. Go ahead. Tell me. How can I prove that these two triangles are congruent?
Yes, sir. AC is common to both.
AC is common to both, but AC is for the whole thing. I'm proving this small triangle here, ABP and CBP.
Oh, okay, sir. I can try now. I think I have.
Hold on. Who was Suchita was the one speaking? Is it?
Yes, sir.
Yes, Suchita. Go ahead.
APB is equal to CPB, which is
Wait. Slowly. Let me write that down. APB is equal to
angle CPB.
CPB. Why? That's equal to 90 degrees. Yes or no?
Yes.
How? By construction, because I constructed it that way, right?
Yes, sir.
Very good. Next, what else can you say?
Angle BAP is equal to angle BCP.
Okay, BAP is equal to angle BCP. Am I right?
Which is theta.
Which is theta, and we know why that is theta because we've already established, because this length AC is common to both and this height is equal in both. So obviously this will be the tan inverse of h by, if you have learned the trigonometry, you know they will be equal. Great. Now what else do you, if the two angles are the same, obviously the third angle will also be the same. Yes or no?
And no, sir, BP is common.
Very good. BP is common. I'm coming to that, but I'd like to, for anybody who has a doubt. So the third angle is also the same, and we have BP is common. Yes or no? So we have established that these two are congruent. Now, if these two are congruent, then I can say that AP will be equal to PC. Correct?
Yes, sir.
And which will establish that P is the midpoint of AC. Yes or no?
Yes.
Did you see that?
That's a nice way of doing that.
Yeah. Somebody said that's a nice way. Who's that?
Oh, that's me only. Sir.
Yeah. So what? You are happy with this?
Yes, sir.
Okay. Good for you. If you find that appreciation, that's the idea. This is not rocket science. This is very simple math. I don't deal with rocket science. I don't know rockets. I don't know complicated mathematics and physics. I know only very simple things. All right. So P is the midpoint of AC, and that is exactly halfway between the two wheels of the vehicle. And the point P has the least displacement from the ground when the vehicle moves up or down on an uneven road. And hence, that's the place which has the least bumpy ride. So if you want to have a least bumpy ride, where do you sit again? Tell me. Where do you sit?
In the middle, sir.
The middle.
Not in the middle. You have to sit middle of what? Middle of my nose.
The middle
between the two tires, sir.
Yes, you have to. So you see, this for me, this has become a ritual now. This has kind of become a ritual for me, right? Whenever, yeah, you can see me now. It's become a ritual. Before I jump into a bus, I always go stand there and look at the two tires. and then I kind of figure out, okay, which is the seat in the middle, and then go inside hoping that that seat is free. Okay, that's always the way I do it. Because you will see, if you get inside the bus, and then if you want to say, you will count all the number of rows, and then you will say there are 11 rows in the bus. If you notice, if you watch very carefully, there are actually 11 rows. And so you will go and sit on the 6th row, which you won't believe will be right next to the back wheel. Okay, and in fact, the least bumpy spot will be just 1 or 2 seats right next to the front wheel. In fact, yeah, that's really the way it works. Okay, so that's it. I mean, in fact, there is one more thing that I want to say, but that's going to occupy quite an amount of time. I don't want to go into that now. Maybe at another instance I would, but instead I would like to throw this open to questions if you have. It is 2:55. We were told a 1-hour session. We started at about 2:05 or something. We still have 10 minutes. Maybe we can extend it a little bit if you all feel so. I'm happy to answer any of your questions now. So you see, just quickly, let me just share my screen once more, right, and just show you. So what is this? So this is just showing, this is the center of the bus, right? This is the very close to this wheel, and this is where you should actually sit. Okay, so next time you get it, and can you tell me in a car where that would be? Is it the front seat or the back seat? Can anybody tell me?
It'll be the middle row.
A middle row. Car has 3 rows. Huh? Your car has 3 rows. My car has. Actually, I don't
would that be like front? Or...
the cars that I get into have
no,
only
it would be in the front. Or
it will be the front seat. You go check it out. The front seat will be closer. In fact, the back seat will be almost on top of the front. And which is the worst place to sit in a bus? Is this last row?
Back row.
It's so far away from the pivot here. Do you understand?
From an experience,
here, and it will just
actually, sir. May I interrupt?
Yes. Who is this?
This is Suchita again.
Yes, Suchita, tell me.
During our field trips, we normally go for the back for the fun.
Yeah, but that has different reasons. You can all gang up together. You don't have to watch what's happening behind you, and you'd only like to deal with what's in front of you, is it not? Huh?
It's mainly to jump up.
Mainly to jump up. I don't know what kind of trips you go to. Yeah, when I was going for trips, we wanted the last row because we wanted to gang up as friends and do our own thing.
Yeah, that's true, sir.
Anyway, so just quickly, just to tell you, see, making connections. Just look at that, right? So you had pendulums, dosa, error analysis, and obsessive-compulsive disorder, right? You had comfortable travel, back pain, and this is 2D geometry. What we just did. Yeah. Okay. I'm sharing my screen. And then, yes, if you have any questions. If you don't have questions, we could probably explore that.
Hello, sir.
Hello, ma'am. So nice to see you.
Lovely to see you.
Thank you for the invite.
Late, but I did start from part of the dosa.
Yes.
And very exciting and lovely. Perhaps you should keep it for our second term, whatever you have.
I will.
We'll invite you back second term.
Yes, I'm happy to. I will. So that's why I don't want to show that.
My connectivity is terrible today.
Yes, but we can still hear you. No problem. Thank you.
Okay,
Thank you very much.
Yeah. Carry on, sir. I'll be right here.
Yeah. So anybody who has questions, any question, you don't have to necessarily stick to this. You could ask just about anything. If I know the answer, I will tell you. Yes, Suchita.
Sir, in our class, we learn about laws of motion and motion in one dimension, and we solve numericals on it.
Yes.
The thing is, like, we get the concept, but the numericals, we're just not able to visualize it. So, can you suggest a way to learn?
What do you mean? You said you are not able to visualize this. What is that supposed to mean?
Like, sir, let me just get an example from the text.
In the meantime, when Suchita takes that, we'll give her the next. Anybody else who has a question, so that we can save some time. Yes, Ranjani. Sorry, Ranjani, I'm sorry.
Good afternoon, sir. Ranjini here.
Good afternoon. What class are you in? What class are you in?
I am a teacher.
Oh, I'm sorry. I'm very sorry. I'm very sorry.
No, that's okay. That's okay. Happy to learn, though. Very engaging discussion, though. It's been many years since I read anything related to physics or maths, but very, very engaging. So thank you.
Thank you. Thank you.
I had a general question.
Yes.
You know, in a professional capacity, I understand that you are passionate about music. I want to understand, how do you make time for your interest and your profession?
Yeah, you see, I have to correct you there. It's not an interest and a profession. Okay. In fact, now it has become. See, I taught for 2 years, and in Gudath where I teach, you see, we try and do everything in house. So much so that we don't even have an administrative team. In NPS, I remember there was a team solely for administration. People are hired just here. Even in Gudath, even the administration is done by the teachers. There is only one accountant and 2 office staff who help with some duty. There are only 3 people. They are just to do the office work. So in a school like this, whenever a program comes up, the teachers have to double up for everything. So you see, when it came up that in the first year and the second year they had to do a musical, and when I gave my CV, I had mentioned that I was trained in Western classical music. So then they asked me, and in 2 years into it, my principal, Meena ma'am, I think I'll forever be indebted to her for that. She is the one who pushed me into it. I was very reluctant. I was very, very reluctant to do it. But she pushed me into it for 4 years. It was a huge struggle. And after the 4 years, I went and told her, I don't want to teach music anymore. And then I don't know what happened. 5th year onwards, then I came to NPS. That was a big turnover. So now it is full time. I am a physics teacher. I am a music teacher. So you cannot say that one is a passion and the other is. But in fact, I have to spend more time learning up music, because you can't repeat the same thing again and again. Yeah, physics is the same. Since the 16th century, second law of Newton has been second law of Newton only. So that is not going to change, and you're going to teach the same thing again and again. So there's less preparation involved in physics and more preparation involved in music. Right. So that's how I find the time. I don't have a choice. It's an occupational hazard. Yeah.
All right. Thank you. Thank you so much. I look forward to meeting you in person. I've heard so much about you from Meenakshi ma'am, Sudha ma'am, Prabha ma'am. Yes. I truly look forward.
Thank you. Yes. Can Subchita, could you take it from there? You had a question?
Hello, sir.
Yes, Suchita, go ahead.
Yes, sir. So the question is, spacecraft flying in a straight course with a velocity of 75 kilometers per second.
Hold on, just hold on. Could you speak up? I can't hear you clearly. Could you speak up? In fact, I would like to write this down as we speak. All right.
A spacecraft.
Spacecraft.
Flying.
Hello?
Yes, sir. Yes, sir.
Yeah, go ahead.
A spacecraft.
Yes.
Flying in a straight course.
Okay.
With a velocity of 75 kilometers per second.
Okay.
Fires its rocket motors for 6 seconds.
Okay.
At the end of this time, its speed is 120 kilometers per second.
Okay.
In the same direction.
Okay.
Find number 1, the spacecraft average acceleration while the motors were firing.
Okay.
7.5.
Just hold on. Yeah,
and number 2, the distance traveled by the spacecraft in the first 10 seconds.
All right.
After the rocket motors were started, the motors having been in action for only 6 seconds.
Okay, I'll come back to this question. I have a doubt. I'm not very clear on that. So you see, what is there here that you can't visualize?
Sir, it's basically when we solve these numericals, personally for me, I'm not generalizing it, but I wasn't able to understand how what's going on and what's happening.
Okay, I will. In fact, solving this should be easy. In fact, I don't want to solve this. Let me instead tell you something else. You've all studied. I think, especially class 9 and 10 finds this particularly difficult. I think this is how you should look at it. You've all studied that distance is equal to speed times the time. Okay, this you've all studied. In fact, I get this equation almost always very wrong, so much so I have to look at the units to make sure that I'm doing the right thing. Do you understand? Right? I'm doing the right thing. Sometimes I say this distance is equal to speed by time, I say, and then I have to go back and then correct myself. Okay. Now this is an equation that you have all learned, and we write it as, say, d is equal to s into t. This we write, and there are many ways to remember. People say you draw a triangle and put distance here and speed here and time here. If you want the distance, then this is speed into time. If you want the speed, that will be distance by the time taken. If you want the time, it will be distance. But these things are all that you already know. But what you haven't really visualized, Suchita, this is what I'm getting to, that this applies only if this body is not accelerating. This equation will apply only if the body is not accelerating. Right? Say, for instance, a body has a velocity of 10 meters per second and it travels for, say, 10 seconds. Okay. Surely the distance traveled will be 10 meters per second multiplied by 10 seconds, which is 100 meters. Yes or no? Are you with me on this?
Yes, sir.
Yeah. Now, what you need, the problem that you are dealing with now, that you are dealing with right now is not this. You have come across a different equation, which is S equals ut plus half at square. You know what this equation really tells you? This equation is actually that previous equation that you wrote, the same equation only with an extra bit. This is the extra bit. See, distance equal to speed into time. Yes or no?
Yes, sir.
Now, you tell me, you're sitting in a car and that car is going at the speed of 10 meters per second and it goes for 10 seconds. Surely you will cover 100 meters. This you know, correct?
Correct, sir.
Supposing you start with 10 meters per second and you travel for 10 seconds, but you are also accelerating at some, say, 2 meters per second square. Then how much will you travel? You will travel this plus a little bit more, right?
Right, sir, right.
That little bit more is this little bit more. Do you understand?
Okay.
Do you understand? And on the other hand, if I were to turn it around and say, S equal, if you're slowing down, you have 10 meters per second, you travel for 10 seconds, right? But while you were traveling these 10 seconds, you're pushing on the brakes. That means now you are going to slow down. You have a negative acceleration. Yes or no? So this thing becomes minus, which means it would have gone 100 meters, but because it was retarding, it went a little less. How much less? This much less. Did you follow that?
Yes, sir. I'm able to visualize it.
Yeah. Now, why don't you try and do these problems with this thing in mind? I think you must be able to figure that out much better now. Okay. Go back and do that rocket car problem. That is here. Of course, it is rather simple. Now look at this. See here. This is a very simple answer because we define your acceleration as the change in the velocity by the time taken. So that's very easy. Okay. So here, of course, in this particular case, it's going to be equal to 120 minus 75 by 6 seconds, right? Whatever that math is, somebody had
7.5.
7.5 what? Donkeys?
Kilometers per hour.
Kilometers
per second.
No, wrong. You were wrong. It's not 7.5 kilometers per second. It is 7.5
kilometers per second square. Sorry.
Per second square. And now this is another thing. People have difficulty. So Suchita, I'll tell you this one more thing and stop. When you say an acceleration is 10 meters per second square, what does this mean? This means it is 10 meters per second. Did you follow that? Means the body will change its velocity at the rate of 10 meters per second in every second. Are you following?
Yes, sir. Oh, okay. Yeah.
Do you understand? That is the meaning of this thing. So in this particular case, you all know that the acceleration, this is the SI unit. So then suddenly when I tell you 7.5, I'm not sure whether it's 7.5. He made a mistake in the unit. I'm not sure he made a mistake in his calculation. I'm just going to assume it's 7.5. Kilometers per second square means what? This means it is 7.5 kilometers per second every second. Do you understand? So now very simple. So now if it travels for 6 seconds, how much do you think? So you'll have to put 7.5 times 6. 7.5 times 2 is 15. 15 times 3, that's going to be equal to 45. So what is 75 plus 45? Oh, 75 plus 45 should give me 120. So correct. Did you understand that? After every second, the speed increases. So that is to say, it started with 75 kilometers per second, right? And then it has an acceleration of 7.5 kilometers per second every second. So this is at time t is equal to 0. After 1 second, it will become 82.5. After 2 seconds, it become well, you have to add that 7.5 to that. What is that? That becomes 90 kilometers per second. Are you following that? Like that, if you finish all the 6 seconds, you will reach 120 kilometers per second. Yeah, that's the speed. That's the meaning of this acceleration. Okay, now I think you'll be able to visualize and do that better.
Yes,
okay,
sir. Very well. Thank you so much, sir.
Good. Anybody else? Anything else?
I have a question, sir.
Yes. Can you introduce yourself?
Sir?
Can you introduce yourself?
I'm Aditya Venkatesh, sir.
Sorry, Aditya Venkatesh. Oh, Aditya Venkatesh. Yes.
It's not related to like studies or anything, sir. Is it okay or?
It's perfectly all right. Go ahead.
I was just wondering.
This is supposed to be like a stress buster session for all of you. Unfortunately, okay, I had to bring in all that congruency of triangles and all that. Anyway, so this is a good break. Go ahead, Aditya.
I'm guys wondering what video games do you play, sir?
Oh, that's the question. I remember. I would like to answer you this question with an experience I had when a very famous personality came to speak in I visited another school for a program, and a very famous theater personality had come, and people started asking her, and she was talking about how she went about creating this big theater in Bangalore. Okay. And she said that she had to let go of many movies offers just so that she can focus on building her theater and getting it right. So somebody got up and asked the question, could you please tell us which are all the movies that you let go? You understand? Well, she very nicely answered the question, but after that, the moderator of the meeting came up and said something I will never forget. When you have a session like this, instead of trying to get information, why don't you try and get some insight? If you want to know the games that I play, I like playing city building games. I like playing flight simulators. I like playing the old Age of Empires and things like that. But there is no insight here. You are just getting some information. What insight would you like, Aditya?
I wasn't really looking for insights, sir. I just wondering, just wondering for fun, sir.
Yeah. So if you ask me, sir, why do you play games? Maybe you'll get some insight, isn't it?
That too, sir. I'm actually wondering that as well.
But
normally you don't see. Normally they seem perceived for like millennials and kids and all that.
Oh well, how do you define a millennial? Do you know?
I mean, like people usually define them as early 20s or late end of teens.
No, the standard international definition is a millennial is a person who was born on or after 1st of January 1984, and I was born after 1st of January 1984, so I am a millennial.
I mean,
okay. So no problem. Well, I play games because I have to be very honest. After I joined work, I have been working for the past 11 years. I've not been able to play like I used to before. But I do find that, especially these last 6 months have been pretty thin because of online classes. We have only a session in the morning. I've been able to, get back to the occasional this or that. But city building games, I like to design things. I like to draw things in 3D. In fact, my house, my kitchen was completely designed by me. I made the drawings and everything and gave it to the architect. And so some kind of designing I like. So that's where all these strategy games and city building games I really enjoy. Flight simulator, so I love everything about flights and flying. My best friend is an Air Force pilot. We as friends back in college, we had music in common. We had physics in common. He was doing physics. He loved music and loved flying. I was into physics. I love music and I love flying. So we connected. But he's the fighter pilot, not me. So yeah, I love flying. So I like to play flight simulator.
So thank you very much, sir. It was really interesting and inspiring, and physics is made, you're really making connections. So you'll start looking at connections now whenever you learn something. So that is what is very important. Then it will be easier for you to understand also. So thanks a lot. Ma'am, thank you for making this session happen for the children. I think children, especially 12th standard children, really enjoyed it. They were actually putting the video on and saying hi to Anand sir. It was really nice to see you. Missed that, ma'am, in the beginning of the session.
Yeah.
So it was it was really good. I know. And Prasanna sir also, thanks sir for all the support, for making the action happen, everything. And children, really thank you so much to making it interactive and cooperating, and being with Anand sir throughout the session. And ma'am, few words from you, and then we will conclude.
All right. Thank you very much, sir. Though I came only at the Dosa session, I found it very fascinating and I was just glued to it. I shall look for that exact seat just like you used to in the bus, and find that spot, come and sit down. Like ma'am said, henceforth, I'll see physics in everything that I'm looking at. And I'm sure children would have enjoyed the session. I saw the connect and I saw the way they bonded. It was lovely having sir with us. I would agree. I mean, all of you would agree with me, children. And we shall call him. Sir is not only passionate about physics and music, but so many other things. And as a human being, he's a fantastic person. Kind and helpful and generous, and goes out of his way to help. For all that, and today it was fortunate that in these times when so many different things are taking place, we could easily invite him over. Physically, I think it would not have been possible. Distances are like that and times are like that. But now we should make use of this opportunity that we can invite, sir and others over so that they can talk. And this was a beautiful informal session where sir had his humor, answered your question. It was truly a memorable time that we had this afternoon, Saturday afternoon, very, very well spent. So could all of you just from yours unmute and give sir a nice clap, please? You could unmute and give sir a clap.
Thank you.
Bye-bye, sir. Take care of yourself. Stay safe.
Thank you, sir.
Thank you. Thank you.
Thank you, sir. Good
Thank
day,
you,
sir.
sir. Thank you,
Bye.
sir.
Bye-bye.
Bye, sir.
Thank you, sir.
Bye, sir.
Thanks, sir.